The fundamental theorem of line integral generalizes the concept of the fundamental theorem of calculus to vector fields. It states that the line integral over the curve depends only on the values of the potential function at the endpoint, not the path taken. If the vector is conservative, then the gradient scalar potential function. This greatly simplifies the computation of the work done by force field along curves and reveals that the path independent is a hallmark of conservative fields. The fundamental theorem of line integral generalizes the concept of the fundamental theorem of calculus to vector fields. It states that the line integral over the curve depends only on the values of the potential function at the endpoint, not the path taken. If the vector is conservative, then the gradient scalar potential function. This greatly simplifies the computation of the work done by force field along curves and reveals that the path independent is a hallmark of conservative fields. Historically, this theorem developed from advanced into potential theory and classical mechanics during the 18th centuries. These pioneers such as Joseph Louis Lagrange and Leonhard Euler providing crucial insight. Their contribution established the foundation of the rigorous mathematical framework that connects motion, force field, and geometry. As scientists equally progressed into the 19th century, particularly with the contributions of George Green, whose work on potential function introduced critical integral concepts, William Rowan Hamilton, who advanced coordination and mathematical physics, and Joseph Willard Gibbs, who synthesized vector notation into logical formalism that formed the base contemporary vector calculus. Green's theorem, on the other hand, concept a line integral around a simple closed curve to a double integral over a region it encloses. This provides the essential link between circulation of vector field along the boundary and the behavior of the field within the region. This theorem is not only for computational shortcut but also foundation for more advanced results. For instance, Stokes' theorem and Gauss' divergence theorem. The theorem named after George Green, a largely self-taught mathematician and miler from Nottingham. Green's theorem appears in his 1928 essay, an essay on the application of mathematical analysis to the theories of electricity and mechanism, which laid the groundwork for much more than vector calculus. Depending initially obscuring, his ideas were later popularized by figures like Lord Kelvin and became essential to physics and engineering. We come up to five objectives. First, to understand and apply fundamental theorem of line integral and Green's theorem in solving problems involving vector fields. Second, to explore these theorems can simplify the evaluation of line integral and relate boundary behaviors to error-based analysis. Third, to develop stronger conceptual grasp of the conservative field, circulation, and region-based integration through practical practice. Fourth, to use Maple as the main computational tool to perform symbolic and numeric calculation, visualize vector fields, and verify results efficiently. Lastly, to strengthen mathematical reasoning and interpretation by combining theory with hand-on computational exploration.
Okay, for problem statement in this project, we were given three vector field problems involving line integrals. Two of the curve were open, which are a half circle and a straight line, while the third formed a closed triangle. The objective was to evaluate the line integral accurately using the appropriate method, which are interparameterization or Green theorem. Based on the board of question, which is question 1 and question 2, these help us understand how vector field behave along different paths and how to simplify complex integral using the right technique. Okay, so in problem statement, we use two main methods which are parameterization and Green's theorem. For question 1a and 1b, we use parameterization to express the part using a parameter t, substitute it into the vector field, then compute the dot product and integrate. For question 2, we use Green's theorem because the curve was closed. This allows us to convert the line integral into a double integral over a region inside the triangle. Each method was chosen based on the shape of the part.
For question 1a, we were integrating along a semicircle defined by x squared plus y squared equal to 1 from theta equal to 0 to pi. We use the circle parameterization, which is x equal to cos theta and y equal to sin theta, and find the derivative of x and y. Then we plug into the integral, substitute the expression and simplify it using trigonometric identities. After that, we integrate the simplified expression and will obtain the result 0. For question 1b, we find the vector equation using the given point. From there, we will get x equal to 1 minus theta and y equal to 0, as theta goes from 0 to 1. Then find the derivative of x and y and substitute into the integral. After that, we just integrate 0 from 0 to 1 and obtain the result 0.
Now let's look at question 2. Question 2 gave us 3 points to work with, which will make a triangle if we plot it in a graph. So what do? Is first, we use the Green's theorem, where p dx plus q dx of a closed integral will equal to double integral of q derived by x minus p derived by y. After that, we just do a normal double integration and we will get our answer is equal to negative 2 over 3.
So in part software calculation, we use Maple software to help perform all the calculation. For question 1a, Maple help us substitute the parameter equation, compute the product, and give a result of 0. For question 1b, Maple also help us substitute uh, the integration and gave a result of 0 too. For question 2, we use Maple software to apply the Green's theorem by calculating partial derivative and evaluating the double integral. So the result was negative 2 over 3 and it matched our manual solution. And in conclusion, Maple help ensure our answer were accurate and efficient.
To summarize the result, question 1a will result the integral of 0 since due to the symmetry of the vector field, while question 1b result in the integral of 0 because the vector field is 0 along the path. For question 2, we use Green's theorem to convert the line integral into a double integral because the points are made out of a triangle region. Since the vector field was not conservative, we get an actual value to the integral. Referring to this table, we can see that both manual calculation and computational calculation brings the same result for both questions. In conclusion, we have successfully applied line integrals and Green's theorem to evaluate vector fields across various curves and regions. We have found that symmetry, path direction, and vector field characteristics significantly influence the result of the line integral. We also understand when to switch between line and area integrals for efficiency and clarity. Also, Maple has enabled accurate symbolic differentiation and integration and helped verify results and minimize manual calculation errors.